We're going to learn about an application of implicit differentiation in which we will use implicit derivatives to model related rates of change. Let's start by defining a related rate. A related rate is an equation with more than one variable, which will require implicit differentiation and, as a result, require the chain rule as well. Solving a related rate has 4 basic steps, and even though the problems will look different, we will approach each of the related rates problems the same. Step 1, we're going to write an equation. Sometimes we're given the equation or formula, and sometimes we have to create it based on the information. Step 2, we will differentiate or take the derivative with respect to time. So no matter what variable we're taking the derivative of, it will always be with respect to t for time. So it'll be d of the variable over dt. Step 3, we'll substitute any known values that were given in the problem or that we can figure out given the information. And our last step 4 will be to solve for the unknown or whatever we're asked to solve for. I mentioned in the first step that we'll always be required to start with an equation or formula. And at times we are given an equation or formula, but when it's a basic formula that we're expected to know, we're going to have to come up with that pretty quickly on our own. So I've made a list in the margin of things that we need to have memorized. When we're dealing with units, for area, the units will be squared. For volume, the units will be cubed. Some basic formulas about a circle that we're expected to know are the circumference, which is 2 pi r. The area is pi r squared. A lot of students get those two formulas confused, understandably so. They're really similar. But if you can remember that area is always squared, just like the units are squared, that's a good connection to keep that formula straight. For rectangle, we have perimeter 2 base plus 2 height. You can also use length and width. Area is base times height. And the reason I like to use base and height for a rectangle is because it naturally flows and transitions into the formulas for triangle, which is the area is a half of base height. And I'm sure you've thought about it before. A triangle is half of a rectangle, so that's how these two equations are related. And then the last one we need to know, good old Pythagorean theorem, x squared plus y squared equals z squared. Yes, you can use a, b, and c. I prefer x, y, and z because x and y are horizontal and vertical lengths. So those just transition easily into any pictures that we need to draw and label. Beyond these formulas, if we're asked about a more complicated value, such as the volume of a cone or the surface area of a sphere, we will be given those formulas. So these are the only basic formulas we're expected to know. For our first example, I wanted to start with a basic equation that didn't involve any shapes or dimensions, but rather just to get us used to taking a derivative of an equation with respect to a different variable than you've used before. We've always taken the derivative of all of our equations this year so far with respect to x. So we're just going to try to get comfortable with this dt differentiation. So we're asked to find the value of dy dt, and that tells me right away that this is a related rates problem because it's with respect to time. It does give us a couple values, y equals 3 and dx dt equals 4. Those are known values that I'm going to use later on in the process. But since I was given the equation or formula, step 1 is done for me. Step 2 is I'm going to take the derivative of this equation with respect to time, or dt. I'd like to take it one term at a time because this is new to you. We've got a coefficient of 2 with our x, so coefficients stay when I take the derivative. And when I take the derivative of x with respect to t, it turns directly into dx dt. Our next term after the plus has an exponent, so we'll deal with that a little bit differently. It is going to be a chain rule because any variable with respect to t is going to require the chain rule, as we mentioned in our definition of related rates. So since it has a power, the power is the outside function, it will come down in front, become 2y to the first. So that is my outside derivative. My inside function is the y, and the derivative of y with respect to time goes into dy dt. So basically, anytime you take the derivative of a variable other than t, or time, it's going to produce this dx dt or dy dt, or whatever variable it is, dt. Once I pass through the equal sign here, I identify that I have a very small product here, and we've seen it quite a bit already this year. So I'm ready for it. I've got left d right, so I copy my x. My derivative of y is dy dt, since it's with respect to time. Product is plus, and then I copy my right, d left, the function x, goes to a derivative of dx dt. At this point, I could do a bunch of algebra and try to get dy dt isolated because that's what I'm trying to find. But it's easier if you plug in the values, substitute the values that we know, because it creates an equation with a lot less variables. So let's do that in our next step. So I used both values that I had. Every time I saw a y, I substituted in a 3. And each time I saw a dx dt, I substituted in a 4. Both of the dy dt's are unknown. That's what we're going to solve for in the end. But you'll notice that we have one value that we weren't given, but we need to proceed past this point. So when you have an original variable that you need, what you do is you use the original equation to solve for it. So since we have the value of y, we'll be able to plug that in, and it'll help us solve for x. So let's go on the side and do that now. So I went back to my original equation. I substituted the 3 for both the times that I saw the y, gave me 2x plus 9 equals 3x. So I just had to gather all the x's on one side, and that gave me x equals 9. So we'll go ahead and put that in our equation right where the x is. So with my new value plugged in, I simplified all of my arithmetic, and I came up with 8 plus 6 dy dt equals 9 dy dt plus 12. I was running out of room, so I just copied that step here. So what we'll need to do to solve for dy dt is get all the dy dt's on one side algebraically, all the numbers that are not attached to dy dt on the other side, and then solve. I don't normally like to do 2 steps at once, but since I'm running out of space here too, I decided to move the 6 dy dt to the right to keep my dy dt positive, and then I would have to move the 12 to the left. So once I had done that, I came up with negative 4 equals 3 dy dt. So my last step will be divide by 3. So final answer for our first example is dy dt is equal to negative 4/3. This next example is the classic calculus ladder problem, and I'm not sure how often it shows up on the exam anymore, but I would feel not quite right if I didn't teach you this problem, and it's a great way to talk about right triangles and how it works with related rates. So we've got a ladder leaning against a wall, which doesn't sound safe at all, but we know some information about it. It's 13 feet. The base of the ladder starts sliding away, as you can imagine, at a certain rate of 2 feet per second. And we're asked how fast is the top of the ladder sliding down when the base is 5 feet from the wall. So I want you to draw this figure, and we'll label the 2 values that we know as well as the rate. Since the ladder is 13 feet, it will be our hypotenuse. The base of the ladder is 5 feet from the wall, so that would be the length of the floor between the wall and the base of the ladder. We're missing this side, but don't worry, we'll be able to use Pythagorean to find that out. And then you'll see these 2, I call these action arrows. They're going to represent the rates at which these values are changing. We know that the base of the ladder is sliding away from the wall at a rate of 2 feet per second. So it would be sliding this way, and since this side of the triangle is getting longer, it would be a rate of positive 2. The top of the ladder is sliding down, and this is the rate that we're being asked to find. So I labeled my triangle as horizontal is x, which is 5. The hypotenuse z is 13. Used Pythagorean theorem to solve and found that the y vertical length would be 12. So while Pythagorean helped me find the dimensions of the triangle, when we start looking for the rates of the triangle, we'll have to use Pythagorean by taking the derivative of it with respect to time. Since each variable is squared, we're going to use our power rule. So the 2 comes down, gives us 2x to the first, and chain rule says we have to attach a dx dt, because we're taking the derivative with respect to t. And basically the same thing happens for all 3 variables. I'd like to divide by 2 throughout the whole equation, so it's going to make our values smaller as we work ahead. And let's plug in our values for x, y, and z. So I have 5 times dx dt, that's the rate of change of the x length that was given to us as 2. We have 12 times dy dt, that's the rate we're looking for. And we know that z is 13, but the ladder is not itself changing. And so the rate of change of the ladder is 0. So the ladder is falling down, but it's neither getting longer or shorter. So I finished solving for dy dt. It ends up being negative 10 divided by 12, reduced to negative 5/6. And derivatives are always a rate of change feet per second.